When I was a kid, every time we had oranges, my dad would always peel this little orange man into the skin as he was cutting them for us, which was quite fun, really. I mean, like, you get to have, like, a little companion. More like a starfish, really.
Here's one Hannah made.
My early one was a bit better. My practice one was a bit better. Some kind of a bend away from you. You actually want your orange man to lie flat on a two-dimensional surface which has 0 Gaussian curvature. So there's no way that two positive numbers can ever multiply together to make 0. And that doesn't really matter so much when you're talking about orange peels or little orange men. But it does matter when you really want to make the surface of a sphere lie flat on a two-dimensional surface, like when you're trying to make a map of the Earth. Okay, so one option, this map here doesn't preserve direction very well, and also it's not going to be particularly useful for navigating. I mean, you're kind of coming off here and there's this massive gap. It's just not very nice, not particularly nice. So this is very squished at the top. So if you kind of look at the top here, the shape of the land, of the coast, doesn't quite match the shape that you get up here. But also, actually, if you sort of imagine, okay, well, around the equator, these squares of latitude and longitude are quite square, and that's quite nice. Maybe we want to try and keep that. So when you go up the top, maybe you say, okay, well, why don't we deform these areas so that they're always a nice, neat rectangle by the time it gets to a piece of paper. For that, you end up with something that looks like the equirectangular projection here, which is certainly the world, and it's, you know, successfully on 2 dimensions. But the problem with this one is that direction goes all over the place here. So if you take one of the ones near the North Pole, this line here is actually really tiny when it is on the globe. So if you want to get from one corner of this to the other, you'd end up going in like this very weird path. It's not very good for navigation. So that leads to the map that probably most of us know, which is made by instead taking a big sheet of paper and forming a cylinder around your globe. Now, you can imagine that you've got a light on the inside of this globe that's right in the centre and shining outwards. And then if you traced the shadow of the land on the paper as it was wrapped in a cylinder around, you would end up with the Mercator map projection. This is what Google Maps uses, and it does a really good job, especially keeping the shape of the countries quite nicely and also in preserving direction. So this is really good for navigation. If you want to get from London to Brazil, you can just head in a straight line. It might not be the shortest way to get there, but you know you're going to get there. So that's kind of why the Mercator map projection is quite handy. The only problem about Mercator, because you're using a cylinder, things are going to be distorted at the poles much more than they're distorted at the equator. And as a result, the area of different land masses ends up being completely mucked up, completely skewed. So if you look on the Mercator map, Greenland and Africa look roughly the same size. But when you look on the globe, Africa is absolutely bloody massive, and Greenland is teeny tiny. So it skews your perceptions altogether. Another one is that Australia, sitting just below the equator, the top bit is anyway, is actually the same size as the entirety of bloody Europe on the real globe. But I think it just ends up, you get a bit distorted when you look at things on a Mercator map. There's still a problem here, right? Mercator's not perfect, there's always going to be a problem. And I spotted something, it's a paper that I've liked for a long time. It's this paper here, it's called Orange Peels and Fresnel Integrals. And essentially in this paper, they show that if you peel an orange in a spiral and then lay it flat on a table, 2 very nice things happen. First off, as your number of loops in your spiral tends to infinity, the shape that it makes on the table tends to a Euler spiral. This very, very beautiful, neat mathematical shape where the curvature changes linearly as you move along it. Really just a lovely idea. Also, the amount that your orange peel has to deform to lie flat on the table tends to 0 as your number of loops in your spiral tends to infinity. So I think we've missed a trick here, because I think that this is what maps should look like. I think that we should prioritise mathematical beauty over geographical practicality.
What is it doing that other maps aren't doing?
Well, it's not going to be deformed. All of the other maps are deformed in some way. And also it's a Euler spiral, Brady. What more do you want?
So this is the Euler spiral map, a new way of map. Can we do this?
I don't see why not. I reckon we can cut this one up and see what happens. Like the way you would peel an orange, right? Like if you were doing a spiral in an orange, so start at the top and then just wind your way down. I'm just going to do it on the earth. Start at the top and wind my way down. Why not?
Whatever you do, don't cut yourself.
Okay, did you do a risk assessment, Brady? Okay, I'm going to hit...
So what's your plan? You're going to hit the seam
Gonna hit this one.
at each line of latitude.
Yeah, hit the seam through Russia, okay?
So ideally you'd be doing this really, really fine, but you're...
Yeah. You know, I think I'm going to preserve it.
You don't-
Remember, I have done a finite number of spirals, and the real Euler map projection, as it's now going to be called, would have an infinite number.
It's worth it though, Brady, for the mathematical beauty that will unfold. Okay, I'm going to do the other spiral now, I think.
This kind of works. This kind of works. As a map, I think people could get used to this. Don't you, Brady?
Have them on the bridge of your ship.
It does mean, you know, if you're in sort of Paris and you want to go to Vienna, you're fine. But if you want to go north to London, you do have to do an entire lap of the globe. But, you know, simple sacrifice. So if you had n loops on your globe, so the width of one of these spirals is like 1 over n, this deformation reduces like 1 over n squared. So, you know, you're gaining. The more loops you have, the more you gain.